Have the rest of the day to work on your homework, and you probably won't have homework over the long weekend. All right, so here we go. So guys, this is all review. I would encourage you not to write it down because I'll bet you already know this. If you don't, be judicious in what you write down. So guys, metals, where are they on the periodic table, the left or the right? They're on the left. And because they're on the left, and because we remember that as you move left to right, they get smaller and weaker, or smaller and stronger, we remember that the metals are big and weak. And because they're big and weak, what do they do with electrons? Give them away or take them in? Give them away. So guys, these things are electron donors, and those are the dudes that form the cations. You good on that? Okay, then guys, in contrast to that, the nonmetals are small and strong. They are electron acceptors, and they form the anions. You good with all of that? Okay, so how does this go down? When a nonmetal gets together with a metal, we know they bond together ionically. How does that go? What does the nonmetal do to the metal? Steals its electrons. That makes the nonmetal negative. That makes the metal positive. Positives and negatives attract. They stick together ionically. And what do we call those compounds that are formed? Salts. Is it all coming back to you? Okay, so guys, these form salts. So today we're going to figure out a system for writing the chemical formulas for salts. So in order to do this, these are the things that you need to know in background, and this is where you want to start taking notes. So first of all, if we're going to write chemical formulas, we really ought to know what a chemical formula is. So let's define it first. Guys, chemical formulas are simply expressions that are used to represent compounds. And guys, these expressions contain two types of information. They tell you what type of atoms are bonded together, and they tell you the ratio that these atoms are bonded together. So you talk about table salt, and you know that table salt is NaCl, so you immediately know what type, sodium and chlorine, but you also know that it's 1-to-1, 1 sodium to 1 chlorine. Unlike water, which you know to be H2O, so you not only know it's hydrogen and oxygen, but you now know that it's 2-to-1. Kind of get the idea? So, what is this going to look like for us? Don't write these down, but here's the idea. Guys, this is a substance called aluminum nitride. It's actually a mineral. It's a crystal. I used to have some, and I have no idea where it went. It's really pretty, but it's called aluminum nitride. So guys, what do you know about aluminum nitride from its chemical formula? What's it made of? Aluminum and nitrogen. And it's not 1-to-1. For every 2 aluminums, we got 3 nitrogens. You get the idea? Okay, so if we look at something like calcium fluoride, which they put in toothpaste to make your teeth stronger, you not only know that it's made of calcium and fluorine, you know it's in a 1-to-2 ratio, so 1 calcium bonds to 2 fluorines. You get the idea? Straightforward, right? Okay, now what about something like this? Guys, this is what we're going to talk about on Tuesday, because some of these salts are not this simple. This is actually barium nitrate. You probably don't want to know this, but it's a laxative. Shh, don't say anything. But, so guys, this stuff is called barium nitrate. You'll notice that this is not one atom bonded to another atom, a metal to a nonmetal. It's a metal bonded to a molecule. We're going to talk about this on Tuesday. This is also a salt, but it's what's called a complex salt, and we'll deal with it later. But we can still figure out what it's made of. How many bariums? 1. How many nitrogens? Now let's look. So guys, the idea is this. There's 1 nitrogen in each NO3, but how many NO3s are there? 2, so there's 2 nitrogens. Does that make sense? We'll talk about it more on Tuesday if we need. How many oxygens are there? 6. So 2 packages of 3. So there's 2 packages of 1 for nitrogen and 2 packages of 3 for oxygen. You get the idea? We'll talk about it more on Tuesday if that's not okay. Fundamentally, what you need to know right now is the chemical formulas tell us how many and what. Groovy? Okay. So guys, the question then becomes this. Why is it not always 1-to-1? Why is it 1 calcium to 2 fluorines and 2 aluminums to 3 nitrogens? Why is it not always 1-to-1? And the answer is this. Remember this guy? The Octet Rule. What does it say? What's the octet rule say? Yeah, they want 8, right? Oct 8. So guys, the octet rule says that atoms are most stable when they have 8 valence electrons. So now we need to do some more review. And guys, it goes like this. In order to talk about valence electrons, we better remember what valence electrons are. So what are the valence electrons? Where are they? On the outs. Good. They're on the outside in the highest, as Josh pointed out, S and P. So they're on the outside. So let's see if you remember the pattern. How many valence electrons do all these dudes have? 1. And these have 2. And all of these have 2. And then do you remember 3, 4, 5, 6, 7, 8? Is that good? Okay. So guys, what that means is, for example, this. If you look at oxygen, how many valence electrons does oxygen have? 1, 2, 3, 4, 5, 6. How many does it want? It wants 8, but to get there it wants to pick up 2, right? You get the idea? Okay. Now guys, what about this? What about sodium? How many valence electrons does it have? It's got 1. So what can it do to get a full 8 electrons? Well, it could gain 7, but why doesn't that work? It's weak. Metals are weak, and metals can't pick up I should always teach in this position. It's kind of comfy. So guys, sodium can't pick up 7 electrons because it's a big, fat, weak metal. So instead of gaining 7, what's it going to do? Lose 1. And how does losing 1 electron give it a full octet? Well, if this 1 electron peels off, what's underneath? The full octet of argon. Now guys, understand that doesn't mean it becomes argon, but when it loses this 1 electron in the 3s, what's left is the full 2s and 2p. That's a full octet and it's stable. So the metals fulfill octets by losing electrons, the nonmetals fulfill octets by gaining electrons, and by knowing how many electrons they have, it tells us how many the metals will lose or the nonmetals will gain. You get the idea? Now here's the beautiful thing. You don't have to think about it, because all of these numbers are on the periodic table, and they are what are called, and you want to write this down, they are called oxidation numbers or oxidation states. You know what? Let's just get rid of oxidation. Wait, what does it say on the periodic table? Oh, it says oxidation states. That's why I put it on there. So guys, we call them oxidation numbers. Most chemists call them oxidation numbers. Whoever put this periodic table together prefers oxidation states. It doesn't matter. Grab your periodic tables though, gang. And they are on the front, not on the back. Look down at the double top secret decoder key down here. Dre, buy a periodic table. You'll like them. They're pretty. See? Okay, so guys, look down in the very tippy bottom, in the very bottom left-hand corner. Where are the oxidation states given? They're the Biddy numbers, right? Right above the abbreviation and below the mass. Do you see it? No? Okay, you're good? I'm hearing no. You're good? Okay, Mason, good? All right. Abby's got you straightened out. Okay, so guys, do this with me. You ready? Don't look at the oxidation numbers, look at the wall. Sodium has got how many valence electrons? 1. What does it want to do with that electron? Lose 1 or gain 7? Lose 1. So when you lose 1 electron, what does your charge become? Positive 1. Now look on your periodic table, and what is the oxidation number that's given on the periodic table? +1. Notice that the plus is assumed to be there. And it's telling you that sodium will lose an electron. Now guys, join me on the wall. Magnesium, how many valence electrons? 2. What does it want to do with them? Lose them. When you lose 2 electrons, what's your charge? +2. Now look on your periodic table. What's the Biddy number? It's a 2. That tells you that magnesium will lose 2 electrons. Good? Now go over to fluorine. Guys, over here, join me at the wall. How many valence electrons does fluorine have? 1, 2, 3, 4, 5, 6, 7. right? So what does fluorine want to do? Gain 1 or lose 7? Gain 1. And if it gains 1, what does this charge become? -1. What's the bitty number on the periodic table? -1. You get it? You okay? Because it gets crazy. Guys, watch this. Look at carbon. Let's do it this way. So carbon's got 4 valence electrons. Carbon is right in the middle. It's almost a metalloid. So what does carbon want to do with its 4 valence electrons? Lose 4 or gain 4? The answer is yes. It does both. So now, how is that represented? And Paxton already saw it. How is that represented on your periodic table? Plus or minus. That's good. So guys, this is the idea. Understand the plus or minus? That carbon could lose 2 or 4. It could gain 4. But guys, it gets even worse. Because what else does carbon have listed as an oxidation number? +2. Remember, the plus is always assumed to be there. So what is going on if it goes +2? It's losing 2 electrons. But guys, here's the deal. I'll explain it in a minute, but the bottom line is this. You don't have to understand why carbon goes +2. You just have to know that it can. But guys, I'll bet you can figure it out. Let me show you this. Let me see if I can do this on the board. These are the These are the valence electrons for carbon. We've got 2s and we've got 2p. And it's got 2 electrons in the s and it's got 2 electrons in the p. So what do you suppose is going on when carbon goes +2? It's losing which 2 electrons? The 2 in the p. So guys, it turns out that some of these atoms can be partly stable by not going all the way to a full octet, but by doing some other things that aren't quite fully there, but they work to make them partly stable. Bottom line is, you don't have to understand it, you just need to know it's possible. So, here's where we are. What do these little itty-bitty numbers on the periodic table tell you? How many electrons they gain or lose. So what is that number going to look like if the electrons are being lost? Will it be positive or negative? Positive, because they're going away, right? And what will the number be if the electrons are being gained? Negative. So then, guys, how do you know which number to use? Look at manganese. Guys, manganese is element number 25. Good stinking heavens, right? How on earth do you know which number to use? And guys, that's what I'm about to share with you, and you want to write these down. These are all the guidance points for how do you know which numbers to use. So guys, it goes like this. First of all, let's define what an oxidation number is, although you already know. Oxidation numbers are the charges that an atom takes on when they fulfill the octet, when they are ionically bonded. So it tells you how many electrons do they gain and lose. Now guys, as you now see, and I don't even think you've got to write this down, some of these elements have got really complicated sets of oxidation numbers. So the question of course, becomes, which one do we use? And you realize you don't have to write these two things down, right? These are just conversational. So guys, here's the answer, and this you do want to write down. The rules are different between the metals and the nonmetals. For the metals, the positive ions, here's the deal. In order to figure out which oxidation number to use, if there's only one, use it, right? Sodium can only be +1. Magnesium can only be +2. Aluminum can only be +3. So guys, if there's only one, you obviously have to use it. But what if there's more than one? Here's the common misconception. Did you notice that one of them is in bold? If you've got to, look at manganese. There's a pant load of them, right? But one of them's in bold. What does bold mean? Well, look down here, and if you look at the key, what does it say bold is most stable? Guys, that's the one that it does most of the time, but it's not necessarily the one you're gonna use. So, how do chemists communicate to each other which oxidation number to use? And the answer is Roman numerals. Do they even teach these anymore? But you know them. So guys, if you don't know the Roman numerals, here's the nice thing. How high do the Roman numerals have to go? Only how high? 8. Really 7, right? Because you can only have 7 electrons to lose. If you've got 8, you're a noble gas and it's game over. So guys, here are the Roman numerals if you don't know them. It's sad to me that they don't teach Roman numerals anymore, because I remember as a 3rd grader just being intrigued by the logic of Roman numerals. Where if you've got a small number, and you know that I is 1 and V is 5, so if you've got a small number before a big number, you subtract it. If you've got a small number after a big number, you add it. So this is 1. This is 2, this is 3, because they're the same size. Now you've got 1, 5, but the 1 is smaller than the 5, so you subtract it and it's a 4. Now you've got 5, now you've got 5, 1, but now the big number comes first, so now you add them and that's 6, and then 5, 1, 1, but because the small numbers trail, you add them and that's 7. You guys all know that? That's brilliant. And you know why they made the numbers like this, right? Because they were easier to chisel. All of the Roman numerals except for C, which must have been a bugger, all have straight lines because they were chiseling them in rock. You're going to say something, Josh? Yeah, that's a great question, and here's the frustration, and my AP students don't like this. So Josh's question was, how do they figure out how stable these things have got to be in order for it to qualify as a possibility? And the answer is this. All of these numbers are based upon electron structures, right? Like we looked at carbon and we said, oh, if it loses those 2p electrons, it could be +2. But that doesn't mean that carbon necessarily does that, because if you look beneath carbon at silicon, you'll notice that silicon has the same electron structure as carbon, right? Same valence electrons, but they don't do the same things. So the answer is, even though something's possible, doesn't mean it happens. So they will not put these numbers on the periodic table until they find a compound in nature that has that particular oxidation number as a part of its structure. It's all done experimentally, because just because it can happen doesn't mean it does. So, you guys good on Roman numerals? Oh yeah, Olivia. Yeah, did you find one? So rhenium is 7 and 3, right? And, oh gosh, and 5. So what does that mean? It means that all of these are equally most stable. That was a really weird sentence. But bold means most stable. Because there's more than one, it must mean they're not only most, but they're pretty equal in terms of stability. So really what it is, Olivia, is a likelihood. Which one are you most likely to find? And apparently with rhenium, you're most likely to find any one of those 3. Yeah. You guys good on Roman numerals? Okay, so what about the nonmetals? Well, guys, the deal is this. With the nonmetals, use the negative charge. In this class, guys, we are not going to deal with salts where the nonmetals go positive. For example, if you look at nitrogen, nitrogen can be like ±3, 5, 4, and 2. Is that right? How do I know that? Good heavens, that's right. Okay. That's sad. Do you guys ever find that your mind is just full of worthless information and the stuff you'd really like to remember just goes away? Yeah, like, for example, the oxidation states of nitrogen. Or the worst example, remember when we did that periodic table lab and you stuck down the boxes and I remembered them from last year? Yeah. Oh crap, I did. That's right. And I can say FPSI, HTL, ZRD, UNG, MCY. Okay, so anyway, so guys, the bottom line is this. If you look at something like nitrogen, nitrogen does have some positive possible charges. But in this class, the rule is this. If it's a non-metal, use the negative charge. But guys, now look really carefully at nitrogen. Where does it start? Plus or minus 3, 5, 4, or 2, right? Here's the thing you got to understand. The plus or minus does not apply to all the numbers. It only applies to the first number. So what charge will we use for nitrogen? Minus 3, and that's it. Is minus 2 a possibility on yours?
Or for nitrogen unleavened.
Oh, interesting. Yeah, we're going to use... Guys, and here's where we get into a little tricky spot. That's interesting. Caitlin's periodic table, which means that some of the rest of yours has this as well. Do you have minus 2 on your table? Okay, for nitrogen. Here's the thing. Depending on the copyright of your periodic table, some list negative 2 as an option, others don't. This one doesn't, and all the ones that I have don't. So let's deal with it right now. Guys, well, let's explain it first. So the version that Caitlin and some of the rest of you have is the most recent version of the periodic table. And remember what I said to Josh? How do the numbers get on the periodic table? They find a compound that contains it. Apparently, since this periodic table, between now and the one that Caitlin's got, they found a compound where nitrogen goes minus 2. So they put it on the table. We're not going to use it. So guys, I just do this. On your periodic tables, if you have minus 2 on there, don't scratch it out, but you may want to circle the minus 3 so that you know to use minus 3. Now let's have the same conversation about oxygen. Some of you have 2 oxidation numbers for oxygen, minus 2 and minus 1. Does anybody have minus 1? Okay, guys, we are only going to use the minus 2. So now, guys, you're going, crap, how do I keep this straight? Nitrogen could be 3, but it's not 2. Oxygen's 2, but it's not 1. How do I know? Guys, here's the answer. And some of you figured this out. You ready? Think through this with me, and you're never going to be confused. How many electrons, how many valence electrons does nitrogen have? 1, 2, 3, 4, 5. How many does it then want? 3. We're going to use minus 3. Oxygen has how many valence electrons? 6. How many does it want? 2. We're going to use minus 2. So guys, the bottom line is this. If it can have, and it's up here, if there is more than one negative charge, use the number predicted by the group. So nitrogen and all of its group mates have 5 electrons. We're going to go with minus 3. Oxygen has 6 electrons. We're going to go with minus 2. So use the negative charge that is predicted by the group. You good? Okay. Guys, we're getting closer. We're actually, interestingly, almost done. But we really haven't learned, well, we've learned some stuff, but we haven't learned how to write the formulas for salts. So now here's what I'm going to do. I'm going to give you some guiding principles for writing the formulas for salts. Then I'm going to give you the steps, and then we're going to do a couple and then call it a day, and you'll get your homework done. Okay? Yeah? For which? Yeah, but those are metals. Yeah, those are metals, or metalloids, so they don't go negative. Yeah, but Olivia, it's the fact that you understood that it was, as you said, a brain fart is a good sign, because you understand that they shouldn't have negatives because they're metals. Yeah. So silicone can it go negative? I can't see it. Yeah, but realize it's a metalloid, so it's sort of, and what you're bringing up here, Olivia, is interesting because you're talking about all the little exceptions, right? But look at where those weird exceptions lie, right on the metalloids, and that's what makes the metalloids so interesting. But here's the bottom line. Trust the periodic table. If it says +4 and +2, it can't go negative. Yeah, you'll always know. Go ahead. Oh, it does? See? And so again, guys, we get into some vagaries. Is that a word? We get into some mucky waters. But here's the thing, as I was saying to Olivia, don't panic. I know that we don't like uncertainty, unless it's with electrons. Sorry, I couldn't pass that up. Guys, we don't like uncertainty, right? But we can always trust our periodic tables. The information that's given on there will always do us okay. Josh is going, wait, but I've got information and that other people don't. At that point, you've got to trust me that I won't put you in that position. Okay. Okay. So guys, here we go. Guiding principles, general rules for writing ionic formulas. Now guys, here's the thing that's nice about these. I'm going to give you 4 guiding principles, but you already know all of these. You know how I know that's true? Because you're smart. Guys, oh, hold on. The reason I know that's true is because I know y'all know what's inside that jug. Table salt. And guys, what is table salt? NaCl. And what do we call it? Sodium chloride. Yeah? Okay, guys, don't let your education make you dumber. You walked into this room, you walked into this school, however many years ago, knowing that that's table salt, and it's sodium chloride, and its formula is NaCl. Now let's apply it to this. Rule number 1 is this. When we write chemical formulas, they are always cation first. How did you already know that that's true? You knew that that was true because this looks stupid. Right? Sodium chloride is not chlorine sodiumide. It's always cation first. But did you notice that's nice? Because where are the cations? On the left. Where are the anions? On the right. And we read from left to right. So they're always in the right order. Rule number 2 is this. All salts have a neutral charge. Now guys, this one's a little more obscure, but you already kind of knew this because you know that this is not sodium chloride. This is not table salt. So why, when sodium and chlorine get together, does it go 1 to 1? Well, guys, think about this with me. How many valence electrons does sodium have? 1. What does it do with it? Gives it away. How many valence electrons does chlorine have? 7. What does it want to do? Pick up 1. So guys, sodium loses 1, chlorine gains 1. That makes sodium plus 1 and chlorine minus 1, and they cancel each other out, and it's sodium chloride. That's why it's 1 to 1. Rule number 3. Rule number 3 is this. When you name salts, the name of the cation doesn't change. And I'm just going to give you 4 right now. The last rule is this. When you name salts with the anion, we drop the ending and add IDE. But guess what? You already knew these as well. Guys, what is table salt? Sodium chloride. It's not sodiumide chloride, and it's not sodium chlorine. See, when we name compounds, when we name salts, we don't mess around with the cation. It's sodium, not sodiumide, it's sodium. But then with the anion, chlorine, we don't leave it chlorine, we chop off the ending and add IDE, so it's not sodium chlorine, it's sodium chloride. Get the idea? So you already knew those 4 rules. You good to go? Okay, now guys, there's one more thing we need to do before we get into actually how to do this. We need to remember a mathematical concept. The mathematical concept is what is called the least common multiple, or maybe you learned it as the lowest common multiple. Now guys, the best way, because I know it's been a while, the best way to teach this is just to remind you by showing you an example. You ready? So lowest or least common multiple. What is the lowest or least common multiple of these two numbers? 2 is the lowest common factor. Greatest common factor. Is it greatest? Greatest common factor. What is the lowest common multiple? Yeah, see, I knew you'd confuse them. So guys, what are the so here's how you figure it out. The multiples of 4 are 4, 8, 12, and 16, and ... it just goes on. The multiples of 6 are 6, 12, 18, 24, and so on. What is the lowest or least common multiple? 12. This is the place they first come together. Okay? Not common factor, common multiple. You good? So guys, the question is, why do we care? The answer is on the board. These lowest, do you guys lowest or least? How do they teach it? Least? Okay. All right. So the least or lowest common multiple, we use that in here to determine the charge where the positives and negatives first meet up. That doesn't make any sense to you right now, but oh boy, will it. All right. So guys, now it's time for steps. There are 5 steps for writing these formulas. I'm going to give them to you. We're going to do 5 of these together, and then you'll get your homework done, and it'll be a great way to start third quarter. You guys ready for the steps? Steps. You could just write steps. So guys, the steps go like this. Step number 1 in writing chemical formulas. Write the abbreviations for the elements. And guys, if your handwriting is as bad as mine, because I've got every card stacked against me, right? I'm a left-handed guy writing on a board that barely works. If you can read my writing, I'd better be able to read yours. And guys, understand this is not a place for freedom of expression. When you're writing these abbreviations, the first letter's capitalized. If there's a second letter, it's lowercase. Do it right now, because if you do it wrong, it's going to back up on you in the coming days. Step number 2 is this. Determine the charges of the ions, the oxidation numbers. Whoa. Boise, Idaho. You think it's your mom? Yeah. We'll answer it and find out. Let's see. Hello? It is. Oh, hey, how are you? Hey, can I give you, I got your email and I was going to reply to you. Can I give you a call back in just a few?
Sure, I was just going to let you know.
Yeah, I saw your email. I'll give you a call back in a couple minutes. All right, thanks. Yep, bye. I was hoping it was a solicitor, and it wasn't. That was awkward. Okay, but at least it was recorded. It'll be a part of the screencast. Okay. We're actually thinking about doing solar. Have any of you guys done that? Put solar panels on your roof? Do you hate it? We'll talk later. Okay, so guys, you good on step 2? Okay, now step 3. Determine the LCM, the least or lowest common multiple. Once you've got the least common multiple, you will then determine how many of each ion you need to create that least common multiple. Then guys, finally, you'll write the formula using subscripts. So guys, what I'm going to do is I'm going to model this for you. We'll do 5. The last one's tricky. And then you're going to have time to get your homework done. These go quick. So tell me when you're ready. Ready? Ready? Not yet. Okay. Paxton's always our first guy ready to go. Have you noticed that? He's a fast writer. Uh-oh. The race is on. No. We're doing 5 just on the board. You guys good? Yep. Okay, guys, I'm going to assume you're ready to go, so here we go. So this is what this is going to look like in homework, but you're going to want some exposure to this. So write the chemical formulas for these compounds. We're going to start with what is called calcium chloride. We have a lot of calcium chloride in our water around here. It's one of the minerals that makes our water hard. But guys, what is calcium chloride? Well, let's figure it out. So in order to do this, and guys, I would encourage you to write big, and I would encourage you to write legibly, and I would encourage you to write in pencil. You don't have to necessarily now, but it makes these better. Step number one is what? Look up at them, they're right there. Write down their abbreviations. Calcium is element number 20, and its abbreviation is big C, little a. Don't do it wrong. Now, guys, we need the abbreviation for chloride. You'll notice there is no chloride on the periodic table, but we now understand that it's actually chlorine. Is Cl. Just like this. Now, guys, step number 2 is what? Find their charges. So, guys, go look at calcium. What's the Biddy number? +2. So you come right here and you write down +2. Now, guys, you go over and you look at chlorine, and holy buckets. There's 11 different charges. Which one do we use? Negative. And what's the only -1 it can be? -1. And so, guys, chlorine is -1. Now, here's what you're going to do. And guys, watch close as I do this, because this is the conceptual part. We have now got to figure out how to make the +2 calciums balance out the -1 chlorines. So how do you do that? And the answer is the least common multiple. So write down the multiples of +2. +2, +4, +6. Now, write down the multiples of -1. -1, -2, -3, -4, and so on. Now the question is this. Where do the positives and negatives first meet up? The answer is the least common multiple. But where do the positives and negatives first meet up? At +2 and -2. That is the least common multiple. The least common multiple of 1 and 2 is 2. So what does that mean? It means the first place that these will balance out is at 2. Now, guys, watch. This is important. How many calciums do we need to have a charge of +2? We just need 1. Now, how many chlorines do we need to have a charge of -2? We need 1, 2, so we need 2 chlorines. Now we're ready to write the formula, and it goes like this. We need 1, we need 1 Ca, and we need 2 Cls. And notice that we do that with subscripts, and we now understand that calcium chloride is CaCl2. Good? Try another one. So guys, you'll notice that I'm purposefully not answering questions. What I've found is that if we can do another one, then if you still have questions, because sometimes this second example clears up your questions. So if you're sitting there going, I'm not quite sure, do this, and then if you have questions, we'll answer them. So guys, first thing we need to do, and some of you are starting to sort of go this way, because no, these are harder than I make them look. So, okay. So guys, aluminum is element number 13. Its abbreviation is Al. Now, this is new. Sulfide? Sulfide is sulfur. Sulfur is abbreviated S. Now we need step 2, their charges. What is aluminum? plus 3, that's all it can be. Now guys, look at sulfur. Sulfur has a host of charges. Which one are we going to use? The negative charge, which can only be what? -2. Now, guys, now what we need is the least common multiple, the place where they first meet up. So we go plus 3, plus 6, plus 9. Those are the multiples of 3, and so on. This is -2, -4, -6, -8, and so on. Now, where is the first place the positives and negatives meet up? 6. So plus 6 and -6. And now, guys, let's see if we can do this a more economical way. Check it out up here. How many aluminums make plus 6? 2. So we're just going to go Al2. Now, how many sulfurs make -6? 1, 2, 3. So that would be Al2S3. You good? Okay. Now let's answer questions. What do we need to talk about? Promise? Okay, then guys, let's do this and see if we can even further streamline the process. You know what? Hold on a second, guys. Something weird happened here. That shouldn't be there. Oh no, we're okay. Okay, so here we go. So guys, now we're going to do iron nitride. And you know what? Maybe I should do this, guys. Yeah, hold on. Let's go back for a second because this is worth mentioning. If it's appropriate for you, okay, we've gone back to the aluminum sulfide. Guys, you don't necessarily have to write out the multiples. If you can look at plus 3 and -2 and in your head go, the least common multiple is 6, therefore I need 2 aluminums and 3 sulfurs, that's just fine. You don't necessarily have to write out the multiples. That's up to you. Okay, so now with that done, let's do iron nitride. So guys, here we go. Iron, is it element 26? Okay, iron is Fe. Iron is Fe. What is nitride? Nitrogen. Now, gang, we need charges. And you go look at iron, element 26, and what's its charge? 2 or 3 or, which one do we use? We don't use the bold one. We don't use the middle one. We don't use the first one. We don't use the one that's predicted by the group. We can't do this. We're stuck. There is nothing in this question, this formula, that lets us do this. We're stuck. The reason is because that's broken. Guys, look back in your notes. How is it that we are led to know which charge to use if it's the cation? Roman numeral. So guys, this has got to have a Roman numeral or you can't do it. So guys, watch on the board. I led us into this stuck spot on purpose. This thing needs a Roman numeral. And now we can do it. Because now, guys, when we look at this, we find out that iron can be 2, 3, or 6, but which one do we use? The Roman, and guys, this doesn't mean the second one. It means use plus 2. So this is plus 2. So guys, here's the beautiful part. Think about this. If you're given a Roman numeral, you don't even have to look at the periodic table. Unless you don't know the abbreviation, just write down the number. Now guys, nitrogen. Nitrogen is element number 7. Can be plus or minus 3, 5, 4, or 2. What do we use? -3. So now guys, let's try this. See if you can do this. What is the least common multiple of 2 and 3? 6. So how many irons do we need? 3. And then how many 3s make -6? 2, so Fe3N2, and there you have it. You guys good? Go ahead, Mason. Look at calcium. Look on your period. Guys, brilliant question. Why did we not need a Roman numeral for calcium or aluminum? Because it's only got one choice. If there's only one choice, the Roman numeral is redundant and therefore wrong. So this is all about efficiency. So if you don't need one, don't put it. If you do need one, it has to be there. Okay. So guys, you've got your homework in front of you. We've got about 20 minutes. You should get it done. I'd love to help if I can. That's not, no. Okay, guys, let's make sure we're clear. All we're doing is the front page of the packet. Yeah. You can't do the back.